All right, so this is hashing. This is a really important foundational topic in computer science. You might think, there's not, how likely is it going to be that I'm going to be implementing my own hash table or something? But there's more to it than that. You see it all the time. You see those like get commit hashes are hashes. Transaction hashes and like crypto stuff are hashes. And of course, hash tables, you need to understand how they work so that you can understand their performance and their trade-offs and do engineering tuning of hash tables for your performance needs. So let's go into it. Hashing. A hash function is a mathematical function. I'm sorry if you don't like math. It is a mathematical function. We're going to have to talk a little bit of math at the beginning here. It is a function which maps arbitrary input, so all the integers, onto small numbers, which we call hashes. Here's an example below. SHA-1, it is a hash function which takes any data as input, so as large as you want, unlimited length, and outputs a single 20-byte number, which we render in hexadecimal. Here's an example. I'm echoing, "Hi there, I'm Riley Ann," into SHA-1 sum, which is a command line program that computes SHA-1 hashes. And I get this 20-byte number out. This is the hash of "Hi there, I'm Riley Ann," exactly as rendered here. Echo, it's very nice to meet you. I get a different hash. Here I'm also displaying an image of Satori from Toho, and it is large. It's 5 megabytes, but we can compute a SHA-1 hash of it, and we get a 20-byte number out. We call these, by the way, when we render in hexadecimal, fun fact, a single hexadecimal digit implies base 10, but a single hexadecimal position is called a nibble. Like you're nibbling on something. It's a small little byte. It's a half of a byte. It's 4 bits instead of 8 bits. And there's 40 of them, so that adds up to 20 bytes. Now, there is, of course, a problem here, because we are mapping a 5 megabyte PNG file onto 20 bytes. Our domain is all the integers, and our codomain is just the integers from 0 to 2 to the 3rd to the 20th. So there's going to be, 5 megabytes is, 40 million bits, I'm sorry. So we have 2 to the 3rd to the 40 million mapped onto just the numbers that cover, so we have 2 to the 8th to the 40 million numbers mapped onto 2 to the 8th to the 20 numbers. We're mapping a shitload of numbers onto a lot fewer numbers. And this is like the pigeonhole principle, right? There's only so many pigeonholes. You have a vast number of possible images that you could hash. And you have a relatively smaller number of hashes that you could possibly output from this thing. So we're already seeing that, hash functions sort of destroy information. You can pass in a shitload of information and get out just 20 bytes. It's like destroying some of that data there. And in the process, it's mapping multiple different input values onto a single output value. It has to. This is the pigeonhole principle. That if you have 10 items to put in 9 pigeonholes, there's going to be 2 items in one of those pigeonholes. There's not enough holes to put one in each one. So we're trying to map too large of a data set onto small numbers. There's going to be collisions. That's just the nature of hash functions, and that's the first thing you need to understand about them. So, properties of a good hash function. They are deterministic. So if I send "Hi there, I'm Riley Ann" into SHA-1 sum to get the SHA-1 hash of it, and then I send the same data in later, I'll always get the same output. So it is deterministic. There's no randomness here. The same data always hashes to the same hash. It is sensitive to changes in the input. That means that if you slightly change the input, if I capitalize my name, Riley Ann, in that string, then the hash will look different. That is important. It is good at distributing inputs uniformly across the possible outputs. I'm not going to show it, but I link a video here in the slides if you want to open it on GitHub to a pseudo-random number generator that Knuth shipped on in volume 2 of the Art of Computer Programming that has this awful distribution where you can see like it looks kind of randomly distributed, but if you plot it in 3 dimensions and look at it from a certain angle, you can see that all the points are like aligned on planes. So it does not actually cover the whole space. It only covers this subset that like occur on planes in 3 dimensions. And this is not good because we're wasting like all those empty spaces between the planes. We want to map to uniformly, if possible, across all the possible hashes so that we fill up our space of hashes. And we don't have these predictable, like, oh, nothing will ever hash to the space between the planes. We want to uniformly cover all the possible outputs. Just math function things we're talking still. And fast. These other properties are hard to obtain, and people put a lot of effort into designing good hash functions, but they also put a lot of effort into the engineering of what if we sacrifice on some of these other characteristics. It has to be deterministic. You can't get rid of that requirement. But you can have, maybe we're not so good at distributing inputs uniformly, and we can just like sort of cheese it a little bit and have a very simple hash function that's fast, which might actually be better engineering-wise in some cases where we just need something that's fast because we're going to be doing it a lot in the security or whatever. The mathematical properties of this thing aren't so important. We still get the performance that we want, especially when the whole point, if you're doing hashing for performance, you don't want your hash function to be really expensive. Like there would be no point. So you have to have some engineering trade-offs here. Sometimes hash functions are used for security things. Git commits are ideally, you shouldn't be able to mess with the hashes and produce whatever hashes you want, or, blockchain uses hashes extensively. You don't want to be able to, double spend your Ethereum or whatever. So there are some extra properties that hashes should have if they are meant to be resistant to attack. So they should be hard to reverse, meaning if I hash, hi there, I'm Riley Ann, then I shouldn't be able to take that hash and obtain the original string. There should be no way to invert this function. If you could do that, if you could invert SHA-1 efficiently, then you could probably make a lot of money by robbing people. And the second property is they should be resistant to collision. We shouldn't be able to find 2 inputs that hash to the same value. A team at Google managed to construct 2 different PDFs with different content. You can see they're different colors, blue and red. But you can see that they SHA-1 sum to the same value. And using a different hash function, you can see that they're actually different files. They only collide in SHA-1. But Google has managed to construct, a while ago, a few years ago, I think, 2 different PDFs with the same SHA-1 hash. And this is bad because a lot of enterprise shit with PDFs depends on PDF signing. So you sign a PDF to indicate oh yeah, this PDF was generated by me personally. My law firm has attested that this PDF is accurate. And they will sign the PDF, and what that is actually doing is just signing the hash of the PDF. And if you can construct a different PDF with the same hash, then you just use their same signature from before. say, oh yeah, this law firm has signed my PDF. Here, it's signed this hash. But it's really a different PDF. It just has the same hash. So, being able to find collisions is bad for a hash function. And in fact, yeah, Google is kind of loud about telling people to not use SHA-1 anymore. They don't use it internally. For this reason, because they've found this collision. It wasn't that expensive either. We're talking like, I don't know, like 1,000 GPU hours or something like that, which isn't that bad at their scale. I wouldn't be able to do it myself, but you know, a state level actor, of course, could do it. The NSA in Fort Meade or whatever, or you know, big tech, sure. All right, so these are our properties of a hash function. You sort of get the idea of what we're looking for in a hash function. I'll explore why and these applications in a minute. But in practice, we have shitty hash functions all the time. Musl is an alternative to libc, and this is the Musl libc, or it's an alternative like glibc or uglibc or whatever. And this is Musl's libc. The C standard library, it has an internal hash map implementation, and this is the hash function that they use. It's really simple. It's just a few rounds of like bit shifts and adds, and here is the just a little piece. I would say about like, I think like 20% of it or something of the code from the Ethereum hash function off of GitHub. And it's complex, and it's got a lot of complicated math behind it, where they wanted very particular properties, and the implementation is really complicated, and it's not so fast. It's kind of been unrolled here, like into a million lines of code, so it looks more complicated than it is. But you can also see that for sure it's more complicated than this little hash function that Musl uses for their hash tables. And that just comes down to engineering trade-offs. For Ethereum, you know, we're talking cryptocurrency. We want security. We want the best security, no matter what it costs. It doesn't matter if it's expensive. With this little hash table that gets used in a few places in Musl, sure, we'll just have something simple. All right, let's get to our first application. When would we use hashes? This is going to be a security thing. So here's our scenario. The last time that Alice saw Bob, she whispered a secret key in his ear, "I am yours forever." That's going to be our secret key. No one knows this key except Alice and Bob. Now one day she wants to damn him a message, but it'd be nice if Bob could be sure that Alice is sending a message at all. Like, she could be asleep, and it could be some fed in Fort Meade or Langley or something, like fucking with them. He wants to be sure that she's actually sending a message. And so this is called authenticity. We want to make sure that Alice is the one on the other end. He also wants to be sure that her original message hasn't been tampered with. So she might be the one sending the message, but if it's been intercepted halfway and altered, then that's no good either. So we want to ensure message integrity. And HMAX let us obtain both properties at once with one trick. Here's the trick. We use the SHA-3 hash, which has some nice properties that we'd like to have for this. We don't have to do like double hashing and padding and weird stuff. So along with the message, send the SHA-3 hash of the secret key concatenated with our secret message, or our message. So we're just sending the message in plain text. We're not encrypting it or anything. We only want the properties authenticity and integrity. We don't want secrecy at this point. We're not going to talk about secrecy. So in addition to our message, which we send in plain text, we send the SHA-3 hash of the secret key concatenated with the message. That's all you have to do. And Bob can be sure that the message is authentic and it hasn't been tampered with, just by sending this one hash. So on Bob's end, he receives the hash and the message in a DM. He knows the key that Alice whispered in his ear, "I'm yours forever." And so he can validate the message by himself evaluating the hash of the secret key concatenated with the message. He just does this. You can type it into a terminal, SHA-3 sum of "I am yours forever," and then paste the entire message in and see what the hash looks like. And if it's the same hash that he got from Alice, then it is an authentic message that has not been tampered with. The hash proves it. The hash is the signature here. She has signed her message with this hash. Why does it work? Well, for one thing, no one eavesdropping on this conversation can actually recover the secret key. There's no way to get "I'm yours forever" out of the hash because there's no way to reverse the hash. There's no way to invert that function. Again, like, Google did find collisions and stuff in SHA-1, but it's still very expensive to like actually reverse a SHA hash and like find a collision with a specific hash and like look through all the set of possible collisions and figure out which one is likely to be the actual original, like which one contains a message in the input. So you cannot reverse a hash function that is a cryptographic hash function like SHA. So there's no way to recover the secret key "I'm yours forever" from the hash. And without that key, the attacker could alter the message in plain text, but the signature is not going to match the message because they're not going to be able to construct the hash. They're not going to be able to provide the corresponding hash value, SHA-3, of the secret key plus their evil message, their tampered message. They can't provide a hash that signs that message because they don't know the key. So the properties of hash functions have allowed us to sign a message and prove authenticity and integrity just by sending the hash of the secret key plus the message. This is called an HMAC, a hash-based message authentication code. And this is often used. Yeah, you see this all the time. Well, I don't know about all the time. Like, it's not a day-to-day thing in your job, but like, you might be working on some code that works with HMACs to validate, whether data was, is valid and authentic and hasn't been changed. You can send HMACs along with like requests to make sure that they are sent by a valid user or whatever, or signed by. I mean, key exchange is a little tricky because you have to get this "I'm yours forever" key to someone else in the first place. But that's not an uncommon scenario. You might just have a secret key already. So that's HMACs. It's a cute little thing you can do with hashes, and you can do it with your friends too if you need to. Make sure that if you're paranoid about feds or something. All right, let's get to the main application that I want to cover, which is hash tables. This is another thing in computer science that uses hashes. Here we're not caring about cryptographic properties anymore. We're going to be using the cheapo, shitty hash functions that anyone can write in their sleep, or just like pull something off the shelf, whatever's fast. Or look something from Wikipedia. Who knows? You don't have to be paying some audit company to do some $1 million audit of your hash function in this case. All right. So here's our problem that we're going to solve with hash tables. We have a set of keys and values. So we have key value pairs, basically. We have a set of key value pairs such that all the keys are unique. And we want to store this and also provide efficient lookup of the value that's associated with any key. So given a key, let's efficiently find the value that's associated with it in the table. And this is, of course, just map from JavaScript or, in fact, regular JS objects. JavaScript objects are hash maps too. You just have the property name is the key and the property value is the value. And it provides constant time lookup of the value given a key. So our naive solution, if we didn't know about hash tables, right? If we're just on our first day of computer science classes, our idea might be to just store all the key value pairs in an array, and we can maybe sort them by key and do binary search, or just do linear search every time. and look up the corresponding value for a key that we're given. And that would be big O of n to find the key given a value. And if the key is not in the hash table, or in this case, it would just be a lookup table, I guess, then we have to go through all n elements and say, oh yeah, none of them match the key, where it's not there. But, on average, it is big O of n. And that's the worst case time too. A better solution, if we know about hash tables, is to allocate one big array and then hash the keys of everything we put in the array to determine exactly where in this array we're going to put the values. So now we've hashed like some key and put it at the corresponding spot. Hash another key and put it in the corresponding spot. And now if we want to look up one of these keys, we just hash it and we know exactly what spot to go to. We don't have to search around. We know right where it goes. Note that there is an ominous asterisk there on searching. We'll get to that. But for now, let's just pretend that we don't have to do any searching. We will just go straight to the exact index, because the hash tells us where to look. We can just hash whatever keys we're given, and it maps straight to one of the values in the array. So let's take a look at what that looks like. So for this example, we're going to use a really simple hash function. We're going to use just the sum of the ASCII codes of the characters in the string. So our keys are going to be strings, and our hash function is just going to be to sum up the ASCII codes. So ASCII, capital A is 65, capital B is 66, and so on. We'll just use all capital letters, it'll be easier. And our table is going to be an array of size 10, n equals 10. So we could hold up to 10 key value pairs in this table. So let's start by inserting the key moon in the value cheese. What we start with is calculating the hash of the key. So the hash of moon, we just add up our hash function is to add up the ASCII code to the characters. So that's 77, 79, 79, 78. And we get 313. So how do we map 313 to our 10 entries in our array? We use the modulus operator. If you took, elementary number theory or something, you'd be super familiar with modular arithmetic. If not, A mod B, that's how you read this, A mod B is the remainder when you divide A by B. So you can divide A up into groups of B size, and at the end you'll have some number left over that's less than B. And that's exactly the property that we want. We need to have this huge number, this hash, which in this case is just 313, but in the case of SHA-1, it's 40 bytes long. And we need to map that to just the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And so we just divide it by 10, and we take the remainder. It's basically taking the last, significant digits of the hash. The last n-1 significant digits, or last log of n-1. No. Yeah, that's right. Log of n-1, yeah. So here's our example. Let's get back to Earth. Table, our array, the index 313, which is our hash, mod 10. And we set that to cheese. So if we do the math here, 313 mod 10 is just 3. We're taking the last significant digit. It makes it easy for our example. So 313, the remainder when we divide 313 by 10 is 3. So we're setting table 3 to cheese. Now our table looks like this. Table 0 is undefined, 1 is undefined, 2 is undefined, 3 is cheese, 4 is undefined, and so on. So here's the code. We just set table index hash of key mod n equals our value. So we've slotted cheese in at 313 mod 10. That was a lot. But I think it follows, We're hashing the key, we get 313, we do mod 10, and that's the slot where we put it. That's what we're doing. So we put cheese in there. So here's our table that we've just constructed. Now we want to look up that key again. We want to look up moon. And all you have to do, of course, is just hash moon. We get 313, take 313 mod 10, and look in that slot. And that's 313 mod 10 is 3 still. It's still the same slot. And so we know exactly where in the array to look. We can look at array 3, table 3, and get cheese out of the table. And that's the value that we're interested in. And so the code looks like just return table hash key mod n. Again, like the key here is that we have like an oracle. We have a secret magic device that is telling us exactly where in the array our data is located. And it's just hashing the key mod n so that it fits within the table. Pretty simple. Let's try something else. Let's insert the key Neptune in the value seawater. So first we hash Neptune, and this is just all the ASCII codes of the characters added up. We get 543. 543 mod n, which is the last digit, because when you divide it by 10, the remainder is just the last digit. So we're going to store it in index 3. But hold up. 543 mod 10 is 3, and we already have something in table 3. The moon is made of cheese, and cheese is in 3. So Neptune and moon, in fact, hash to the same value mod 10. They have different hashes, but we need to fit, like, sort of further narrow down that hash to fit in 10 slots. So we're going to have like even more of a pigeonhole problem on our hands with collisions. And in this case, we have a collision. Moon and Neptune, under this hashing scheme, hash to the same value mod n. So things aren't so simple. We have to somehow come up with some scheme to resolve this hash collision so that two different keys can hash to the same place in our table, and it can coexist. Our user shouldn't have to care that we've chosen a hash function that hashes two of their keys to the same value. Like, that's all implementation details on the inside. They shouldn't get, oh, I've gotten an exception because some boneheaded hash map developer made a decision that makes two of my keys collide. What does that mean? You know, we should be able to just accept this input of like one key is moon, one key is Neptune. Sure, they collide, but we'll figure something out. We'll find some place to put it, right? We'll handle it. And so we've got to come up with some scheme to make that work. Somewhere to put our data. Of course, up to this point, we've been pretending that every hash is going to map to a different place in our table, but that's not true. Especially as the table fills up, it's not going to be true. And there are many approaches for dealing with this problem. I'm going to cover 3 of them. Of course, you can only implement one at a time in a hash table, but you'll at least get a feel for the different approaches that are on the menu if you want to implement your own hash table. And the code on GitHub for this, I've implemented a hash table myself for this presentation, and it uses linear probing, this first one. So this will be a one that you want to pay special attention to if you want to look at the code. All right, so linear probing, what does this mean? What is linear probing? When we insert some key value pair into the table at a spot that's already full, so that like our collision with Moon and Neptune, we just try the next spot. We just move over one. And if it's full, if it's also a collision, then we move on to the next one, and the next one, and the next one, until we find a free space that we can insert. And we use that one. So it might be, a few spaces later until we find a free space for it. Or it might be just the very next one, who knows? Depends on how full the table is, right? You might have to go quite far. So, similarly, when we want to actually look up at the value given the key, we check the actual, predetermined spot that the hash function indicates. Table 3 in the case of Moon and Neptune. We check that spot. And then if it doesn't match, the key that we're looking for, then we check the next one, and the next one, and the next one, until we find the key we're looking for, or an empty space. That's going to be our scheme. Of course, now we also have to store the values in the table. We can't, or sorry, the keys in the table. We can't just store the values because we have to be able to check, right? Like, oh, is this key the actual one that we're looking for? When we're going like, oh, next one, next one, next one. When we're searching for a key in the table, like, it doesn't do any good to just have the values because we know they all hash to the same thing. Like, there's going to be no way to figure out which value we want unless we actually store the original key too. So we store the values and the keys in the table now. Other than that, yeah, it's just a matter of like when you insert and the spot is full already, you just move on to the next one until you find an empty spot. And when you are looking up a key, you just try the first one that the hash function indicates, and if it's not the one you're looking for, then you try the next one and the next one and the next one until you reach an empty space. That's the like point where you know that the key's not in the table. If you've reached an empty space, because if you've inserted like something that has collided and you've had to do some linear probing, like to put it in a later space, right? You're never going to insert it past an empty space. You're going to take the first empty space that's available. So when you're inserting, you're always picking the first empty space. So when you're finding, if you're like going through one at a time and you find an empty space, you know that there were no, that the thing you're looking for is not past the empty space. It can't be. Does that make sense? Like, you're inserting up to the first empty space. Like, you're done when you find the first empty space. So, like, how would you ever get to the other side of an empty space to insert later? Like, no, you're just taking the first one when you insert. So when you're finding, you can also just give up when you find an empty space. I think it makes sense. All right, so here's an example. We're inserting Venus shell. She comes out of a shell into this table up here. We've got the moon, Earth, and Mars. The moon's made of cheese. The Earth is, of course, made of pain and suffering. And Mars is made of candy bars. Girls go to Mars to get more candy bars. So we're inserting Venus in the value shell. What do? Well, say the hash value of Venus mod 4 is 1. We're doing mod 4 because the table is of size 4. So say it hashes to tell us to look in position 1. So we'd like to insert Venus here, but it's full. So we go down to Earth. That's full too. We go over to Mars. That's still full. So we wrap around and start from the beginning again and find an empty space, finally. And in the end, we put Venus shell into table 0. And this is our, spot where we've inserted Venus. We see that on the next slide, I think. So here's Venus in her shell on index 0. Key Venus value shell. All right. We did have to probe through the entire array to find an open space, which is not good. If you've got 1,000 items in your hash table, it's probably a good idea to not let it fill up to the point where you're having to probe through the entire thing to find an empty space. But we'll talk about that in a second. Let's in fact try retrieving the key Mercury and say that our hash function of Mercury mod 4 is 0. So the first place we're going to look is 0. And we're going to do some linear probing. This one's not Mercury, so we move on to the next one. We have to move on to the next one, because what if this one was full when we inserted Mercury before, right? We have to move on to the next one and check that too. This one's also not Mercury. This one's also not Mercury. This one's also not Mercury. We come around to the start again. We haven't found anything. So we can give up at this point. If we had found an empty space, we could have also given up. But at this point, we know that we've checked all the elements in the table. Come on. Mercury is not in this table, and we can tell the user, we return undefined or something. Or throw an exception, maybe. It's probably a bad idea. But do something to indicate that Mercury is not in the table. But I mean, you notice here that like we're doing a lot of probing. We're like iterating through the whole thing a lot. And that's because the table is full. We have gotten to the point where all or almost all the table has been filled up with items. I mean, our table is very small. But in general, the load factor of a table is the number of items in it divided by its size. So as this load factor in general approaches 1, we end up having to do lots of probing. We don't like this. We don't like to have these like long runs of like, oh, this could be a collision, this could be a collision, this could be a collision, and like having to probe forward and checking more and more of them. Like, this takes time, and it messes with our nice constant time retrieval, right? And so we would like to avoid doing that. So, yeah, we just don't let our table get too full. How do we deal with that? And the table fills up? Or when the load factor crosses some threshold, which is the way that you usually do it. You resize the table. It's called rehashing the table. You basically just allocate a new array for your table and reinsert all the items again. That's it. And you rehash every key to account for like the new size of the table. And just find its new plates and you put them in and you do the same logic with like, oh, there's a collision here, we need to move on to the next space and so on. There'll be some collisions probably. But not as many as before because the table is larger. Here's the rules of thumb. The default that Java uses for its hash... Actually, I did only check the old hash table class where you're supposed to be using hash map now. But at least before, a good rule of thumb was 0.75 is the load factor. And I have seen this elsewhere too, where once 3/4 of the entries in the table fill up with keys and values, it's time to rehash the table and grow it to a bigger one. And when you grow it, you double the size. So you might start with size 10, and you double it to 20, and then 40, and then 80, and then 160, and 320, 640. So those are your rules of thumb. Rehash when the load factor reaches 0.75, and double it each time. And that gives you, you can do some tuning, I guess, if you have some really crazy special need. But this is like tried and true values. Okay. We're done with linear probing. That was like sort of the scheme for, if you have a collision, you just move on to the next space, and you move on to the next space until you find an open spot to insert. Or if you are finding a key, you just check the spot you're supposed to, and then check the next one. If it doesn't match, check the next one, and so on until you find another space. And that's the linear probing scheme for dealing with hash collisions. Double hashing is another scheme to deal with hash collisions. And it's very similar, but it does one key thing different. It makes use of 2 different hash functions, hash 1 and hash 2. This is not that crazy, right? There are different hash functions. I mean, I showed you 2 of them already, SHA-1 and SHA-2. But even in the same family of hash functions, the example code that I have in GitHub for this lecture uses murmur hash, which actually takes a seed, so you can provide it an arbitrary number, and it'll give you a different hash function for each number that you provide it. So there are up to, however many JavaScript integers there are, like 2 to the 52 or something. There's a family of hash functions that has 2 to the 52 different functions in it, and you can just select which one you want. And it all uses a very similar algorithm, just with different seed values. Anyway, double hashing, you have 2 different hash functions. They could just be 2 different murmur hashes with different seeds. First, you try to insert at hash 1 key mod n, just like with linear probing. If that spot is full, then we jump forward by hash 2 key spaces. So, whereas before we jump forward by 1 space every time, just go to the next space, the next space, the next space. This time we're jumping forward by an increment that is determined by the second hash function. So you keep jumping forward by increments of #2 of key with every attempt. Yeah, same as linear probing, but with a different increment. It's instead of 1 every time, it is #2 of key every time. Okay? That's going to be our scheme for double hashing. The con here is, well, first of all, evaluating the hash function twice might be a tiny bit more expensive. Who cares, right? But the big con is that double hashing breaks cache locality. Because you're not just checking, oh, I'm checking this index, I'm checking the next index, I'm checking the next index. Like, that is all in the same, if you pull in some memory into cache, like, those cache lines are going to be, like, it's all going to be the same fucking, like, location in memory. So it's going to be really efficient to just check, like, oh, the next one, the next one, the next one. It's going to be in cache already. But when you're jumping around by increments of #2 of your key, you might be like way over here now, way over here now, way back here now. That's going to break cache locality, and it's going to be expensive waiting on the memory circuitry to retrieve those values for you. It's got to go through complicated pipelines to finally reach your code. The pro for double hashing, this is why you would want to use it despite that con, is that it mitigates clustering. Here's what clustering is. With linear probing, when you're just going like, oh, next, 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 and you try to insert like anywhere in this like crowd, this cluster of existing keys and values, a bunch of stuff has already hashed to somewhere in here and gotten glommed together into this big cluster. Each one of these squares is a table entry index. And the longer this cluster gets, the more likely it is that something is going to collide with it. Like, if you have a very small one, it's unlikely that something's going to collide with this. But it's pretty likely that something's going to collide with this big guy. I mean, it's taking up like 1/3 or something of the entire array. So like, it's pretty likely that a key is going to hash into here when you try to insert into it. And what's going to happen when that happens? With linear probing, you're going to insert into it, and it's going to probe to the end and insert like here. And you're only growing this cluster bigger. And in fact, here it's absorbed part of like another mini cluster here, this just single entry that's just sitting here, into the cluster. So you get quadratic growth of these clusters over time. And these clusters kill performance because like if you're searching for an element that got like shunted from the beginning all the way to the end and you look it up, you're gonna have to probe and check the keys for every single one along the way until you finally find it. And as these clusters get bigger and bigger in the table, it's just creating like more and more opportunities for these long chains of like checking the next one, checking the next one. And it kills your nice big O1 performance. But with double hashing, we have somewhere else to go besides just the end of the cluster. Going to the end of the cluster with like linear probing is just going to grow it bigger. But if we have somewhere else to go that is going to be deterministic, we know where to go, but it's somewhere else. And it depends only on the key. Like, it's going to be different for different keys, so that not all the keys go somewhere else that's the same. It doesn't help us if all the keys go somewhere else, but they all go to the same place. They go to different places. It's deterministic. This is the second hash function's purpose. It gives us somewhere else to go for each key so that these clusters don't grow. So this is our double hashing scheme. We try the first hash, and we look at the spot, and if it's a collision, we check a spot that is offset by the value of the second hash. So if hash 2 of a key evaluates to 3, then we jump 3 spaces. And we try that one. And then if that's still a collision, we try another 3 spaces over. That's the idea. So it has some cons. It breaks cache locality, but it mitigates clustering. In practice, if you look at the performance curves of these things as tables get more and more full, linear probing is more efficient for tables that are not so full. And as the load factor goes up towards 1, then clustering starts to outperform it. So if you keep your load factor below 0.75, for example, that's a good cutoff because that is still at the point where linear probing is better than clustering on average. If you do an experiment and actually check these things, you're not going to be able to intuit it just by thinking about it, but if you can run code and just compare these two things, then linear probing is better over the entire range of load factors from 0 to 0.75 with random data, So just use linear probing, I guess, unless you need, keeping a quarter of your table empty with a load factor of 0.75, a max load factor of 0.75, could be a lot of memory, If you have a several gigabyte sized hash table, you might not want to have your load factor so low. You might want to have it up to 0.99 or just 1. The code that I wrote actually works with load factor 1. You can tweak it and check it out. You can go right up to filling the entire hash table. And that's something you might, potentially want to do if you have very special needs. But in general, as just an application programmer, probably just keep the load factor at 0.75 and use linear probing because it's still better. But we have a problem. So linear probing and double hashing, these are called open addressing methods. They are basically just jumping around in this big table full of keys and values, right? If you find a collision, you go somewhere else in the table. That's called open addressing. You might have different schemes for doing that, but it's all open addressing, and they all have the same problem. Deleting items. This is a pain in the ass. It's not too bad. It's you can screw up your eyes and sort of work on it for a few hours and get this implemented. I had some bugs in my code when I first implemented it. It's not bad, but this is definitely the hardest part of implementing an open addressing hash table. And let's see why. What happens if you delete an element from inside one of those clusters of collisions? Let's go back to the previous slide. So say you delete this element here. We've deleted this. Huh. Doesn't that mess up these elements? I think I have another diagram in the next slide. Yeah. So in this example, this is the same example as before. The hash of Venus mod 4 was 1. We wanted to insert it at 1. But we had to probe across to 2 and 3 and ultimately to 0 in order to find an empty space for it. Say we delete the Earth now. We relieve humanity of its suffering. We're elophysicists and we just want to wipe out human life. Now we've deleted Earth and we try to look at Venus again. Well, the hash of Venus mod 4 is 1, so we check 1. You know where this is going. It's not Venus, so we check 2. And we can't find an empty space. This is supposed to be a sign that Venus is not in the table. It's finding an empty space. That's what saves us from having to search the entire table. If we had to search the entire table every time, then we'd just get worst case big O of n lookups because we'd be searching the entire table for keys that don't exist. We could not abort when we find an empty space. So this is a huge problem for us. We'd like to be able to give up when we find an empty space. But when we delete an element, we create an empty space. What do? You see the problem? Venus got shunted all the way across from where we wanted to put it, 1 to 2 to 3, and then ultimately to 0. But if we break the chain, if we sort of get rid of this element, then when we go look up Venus, there's going to be no way to tell that, Venus had been required to shunt past that empty space before we removed the element. It made sense before we removed the element. You could say, oh yeah, Venus might have just been shunted to a later spot because we haven't found it yet. And we found no empty spaces. Now we found an empty space. This kind of throws a wrench into our whole plan. Okay. All right, how do we resolve this? This is kind of subtle. So after we delete Earth from 2, we probe ahead for a key to find a key that could have gone into that empty space. That it would make sense when we're doing a search that we would want to check spot 2 for this particular key. So it could be something that hashed to spot 2. It could be something that hashed before spot 2 that got shunted to spot 2. But we want to find some key that could go there reasonably if we're doing a search for that key. Okay, so say that Mars, the hash at Mars mod 4 was 3, so it's Mars is in the correct spot. We want to fill in this empty space. We have to search past Mars to Venus. This is the Venus mod 4 hashed to 2, so we can just move it to the empty space, and that's going to be our approach. We find some space, some key and value that could go into that empty space, and we put it there. So let's move it. We moved Venus into space 2. But now we have another empty space, and we have the same problem again. We've created an empty space by moving Venus, but we can just repeat the process. We keep going until we find an empty space. Or, well, we're sort of guaranteed to find an empty space again somewhere, because usually the table is not full completely. But, actually, even if the table is completely full, we have just removed an empty space. We have just removed an element, so there is one empty space. So if we find nothing at all that could go there, and we go all the way around, then we will find the empty space. So we're guaranteed to terminate. We will find the space that we just deleted. So in the worst case, there's nothing to put there, but we may find something and have to move it there. Anyway, the idea is to just keep filling in this empty space with something that could go there until, we've marched all the way around to the empty space again. Or find a different empty space. I mean, in this example, there's only one empty spot, but there could be, another empty spot. So we just keep going until we find that empty spot. And it's by the same logic that we had before all this remove nonsense, where once we find an empty spot, then we know that it wouldn't have gone past an empty spot to do an insertion. All that logic still applies. We just have to sort of set up that scenario again in our post-remove world, where we've created a new empty space for ourselves to deal with. All right, does that trick make sense? To just keep trying to fill in the empty space that we create by swapping an element into it. Create a new empty space. Okay, swap another element into it that could go there. That could reasonably go there. And we just keep doing it all the way around. The exact logic for what could reasonably go there looks like is a little bit subtle, but I'll leave that to the code if you want to look at it. That's the part that's hard to get right. Okay. We're done with open addressing methods. The linear probing method and the chaining method. There are other open addressing methods, but we're not going to cover them. So this is a non-open addressing method for dealing with hash collisions, chaining. And you're going to like this one because it's easy. With chaining, each spot in the table in our array just holds the head of a linked list to all the collisions that hash to that spot, So the fourth element in the array is everything that hashed to the fourth spot. If there was a collision, we're not going to go searching for a spot for it. We're just going to append it to the end of the linked list. Pros, simple to understand. It's really simple to implement. You probably already have a linked list implementation lying around somewhere. Cons, linked lists are slow. It's very cool to have just a single flat array that has all the data you need in it. It's great for cache locality. And linked lists, you're jumping all around memory. And you're, the garbage collector is cleaning up nodes or whatever when you do removals. It's just a performance thing. And I mean, you can probably just see the way this works already, but I'll just run through it. When you insert a key and a value, check the linked list at table hashkey mod n to see if the key is already in the linked list. If it is, then update its value. If not, then add the key value pair to the end of the list. Or to the head of the list. Head probably makes more sense. To retrieve the value for key, when you're looking at like get key, look for the key in the list which is located at table hashkey mod n. Yeah, so you just go to this location in the table, you see the head of a linked list, and you traverse the list looking for the key. That's our chaining scheme. It is a lot easier to understand than the other ones, I guess, but you also probably don't want to use it. Because ultimately, hash table is not that hard to implement. You pull it off the shelf, or someone just takes the data to do it. And it's used a billion times. You want high performance, if possible. All right, there's one more thing. Iteration. When you are, when you want to iterate over a hash map, hash table, they're the same thing, by the way. Hash table, hash map. To iterate over it, JavaScript itself keeps a separate array to hold all the key value pairs, which are sorted basically in the original insertion order. So whenever you insert something into the map, it goes onto the end. And whenever you remove something, it just comes out of the array and everything's reindexed. This does add linear time overhead because when you set a value, you need to search the array to find that value and then update its value. Well, you don't technically need to. You could just look up the... you could just keep a set of keys and look up the value in the hash table, and it wouldn't be big event overhead. But it would be big event overhead for the remove operation for sure. Because you have to... because remove on arrays is big event. Even to find the element to remove it, let alone removing it. Okay, so in my code, I also have just a separate array to hold these key value pairs. It's really useful. Here's a note. What are we actually hashing? Hash table keys, well, in JavaScript, they can be anything. They can be objects. They can be, I think they can be arrays. I'm not sure. They can be numbers. They can be floating point numbers or fixed point numbers. Of course, they're the same in JavaScript. If you are hashing numbers, if those are your keys, you can just use the numbers themselves as the hash value. You don't have to run them through a hash function, right? You can just use the number mod n, mod the length of the table, as your, where you're looking in the table. But if you do that, then you should make sure that the numbers are uniformly distributed, like IDs or something. IDs are good because they're all different. But if you have a million items that all have the exact same number, and that's your hash function, then that's not going to be any good. Although, really the issue is that they might be very similar numbers. Because even if they're the exact same hash number and you use a real hash function, then they're all going to go to the same place anyway. But if the numbers are just very similar, if you've got a bunch of zeros and a little less ones, and it's half normally distributed or whatever, then you're going to have like a big cluster in your table around the most common values, and that's not good. So you want to either make sure the numbers are uniformly distributed if you use them as a hash function themselves, or just run them through a hash function, and then it'll spread out the numbers so that, numbers that are very close, like I said in that slide way back about being sensitive to changes in input, the number right next to it might hash to a completely different value. So you don't get these big clusters around common numbers, right? Strings are especially easy. The code that I wrote uses murmur hash, which is a common hashing library for this application. And, well, it's not a library, it's an algorithm that is someone wrote a library for in JavaScript. Or we can use objects as our keys, right? This is something that you can do in JavaScript maps. You can't do it in JavaScript objects. So you can't have an object with an object key. Like, objects have to have string keys, right? But you can do that with the map class. You can just put in an object as your key. Now, there's two different, like, semantic meanings to what that actually is. If you want to compare two keys for, like, oh, this key is equal to this key, and you're talking about object keys, like, how do you tell whether one object is the same as another object? There's two sort of ideas here. There's object identity, which is they are literally the same object. Like, if you update one, the other one gets updated too. You can have two different variables pointing to the same object, right? Or like two different nodes in a linked list pointing to the same object as their value, as their data value. They might be the exact same object. That's object identity. And then there's also the question of deep equality. So, like, do the objects contain the same data? If you compare all their fields, the fields themselves might be objects. You can recursively compare those two and say, like, okay, are these two objects the same? But, like, do they contain the same data? We don't care if they're, like, literally the same object. So these are two different concepts. And unfortunately, object identity is difficult for us in JavaScript. The way that this is usually implemented in, for example, Java, if you want to store an object as a key in your hash maps, and you want to use object identity to compare keys, then you can get a hash code for the object. And this is computed based on the object's memory location. So if they are the same object in memory, then they get the same hash code. That's the way that works in Java. But in JavaScript, there's no such facility. You cannot obtain the memory address or a hash of the memory address of anything in memory. And it wouldn't be good for you anyway, even if you did, because things move around in memory. So we're in a bind in JavaScript for using objects as keys with object identity. By the way, the map class in JavaScript uses object identity. If you pass in two different objects with the same content, they will not be the same object. I think I might have an example. Actually, I don't think I do. But yeah, if you store like some object with like the key A and the value B, and then pass in a different object with key A, value B, it won't find it in the default map class because it's using object identity. If we want to reproduce that behavior, that's what this slide is. If we want to key off the object identity, then we can't use the memory address as I noted, but we can sort of make every object unique at construction time. Like, we can keep a static variable in the class that increments every time we do a construction. So every time that we initialize a new myData instance, it's going to get a different object ID. So we can key off that object ID that it gets at construction time, as long as it's constant. Like, it's not, we never update this object ID. It just gets determined when we construct it. And so since all the objects of this class have different object IDs, we can just key off that and use that to like sort of determine object identity. It's like a little bit of a trick. Here's an example of what that looks like. Here's my hash map implementation. I have an argument on the constructor that lets you pass in a function which extracts a effective key out of anything you want. So I'm able to accept object keys, or in this case, a my data key. And you just gotta tell me, like, how do I get a string out of this thing, right? I actually should have a .toString in there too. We're trying to extract a string out of whatever we give us. And that's all there is to it. This is sort of just a trick. If you're doing object equality instead of object identity, like you just care about whether objects are the same, then in this extractor function where you're getting the effective key out of a key, you would get out basically just a encapsulation of all the state of the object, or a hash of it. And so like you're keying off of all the actual content of the object instead of, just the object ID or something, or the object itself. If you don't pass in this function at all in my implementation here, it just uses the identity function. So you can use strings directly as keys, and you don't have to worry about this whole like getting an effective key out of a string when it's already a string. Yeah. Okay. Hash tables was kind of a lot. But it is important, and it's not that bad, I think. I think that was the last slide. I can kind of show some code, I guess. This is the hash map. And I won't go through the implementation of every method, but we can sort of see the general idea from 1,000 feet. We're including the murmur hash library, which we'll be using later. We have an initial table size static constant, which we start at 10. Our max load factor is set to 0.75. This is just a murmur hash seed that determines which murmur hash function we get. And this is going to be random each time, so every hash map is going to have a different set of, different hash function. I could have just picked a constant one, and it probably would have made more sense, to be honest. Sometimes actually you want to use a different hash function each time you rehash when you grow the hash table, so that things that collided under the old size, like if there are lots of collisions or whatever, are less likely to be related to each other after the rehashing. So you might see somewhat better performance if you change this murmur hash seed every time that you rehash when you grow the array. But I'm not doing that. Here's our main hash table array. We just start at initial table size and fill it with undefines. Here's this thing that I mentioned that we use for doing iteration. Like we can just iterate over all the key value pairs in the table in insertion order, which is why we need a separate array for this. So that's what this is doing. Our hash function is just going to call murmur hash, and a function to extract an effective key, a string, from any keys that they want to pass in. So if they say like set of some value that's not a string as the key, and then some other value, then we extract the effective key out of the key using the function that they pass into the constructor here. And this is a way to like allow people to provide like complex objects or whatever, or just like instances of their own classes, which are also objects, as keys in this hash map, as long as you give me a function that lets me extract a string out of this crazy thing you're giving me as a key, then I will take it, I'll handle it, it's fine. I just need to know how to get a string out of it. It's just a nice facility to add to a hash map function, I guess, in JavaScript, when there's no, unless you want to require the user implement a like hashing protocol on all their keys, What you could do, it's kind of, I don't know, it's nice to just be able to pass in a function of the constructor and have it be done with. And be able to handle types like numbers or whatever that murmur hash can't actually deal with. All right. This is just some logic to like run the extract effective key function and make sure we get a string out of it and so on. Setting a key to a value. Extract the effective key out of it. We update the entries array. So we just like sort of find if there's one already there that matches if we extract the effective key out of this key, that it matches our effective key of the key that we're giving here. Okay. I think that makes sense if you just look at it. If we find it, then we update it. Otherwise, we just push a new one. Now we need to update the hash table itself. So first of all, if the table has passed its load factor, if the number of entries has passed, divided by the size of the table has passed the max load factor, or there's just no space at all left, then we grow. The reason for this or is that our load factor might just be 1 and we'll never surpass it. So we need to actually have a case here to, in case someone goes tweaking this default max load factor variable up here, it would be nice to be able to handle that case. So we have a separate, if the table is absolutely full, then we grow the table. We do the rehashing shit. And since we've already inserted it into entries, this grow is just gonna like reinsert everything that's in entries. That's it, we're done. If we don't need to grow, then we also need to just like insert it into the table itself. So we find the spot for it. That's what this function does. It finds like where in the table we can possibly insert it. And it probes forward if the spot is full and so on. So it finds the spot that it's going and sets that spot to a key value pair. We're storing the effective keys, by the way. We're not storing the keys themselves. It just saves us from having to evaluate the extract effective key function every time, because we don't need the key itself in the table. We have the key itself in the entries array already. For when someone wants to iterate over all these keys and values. Really all we care about in the table itself is the effective key, the string that we've managed to extract from whatever crazy key type they give us. All right, and that's it for setting the value, setting key and value. Get is also similarly very simple. You just find a spot for the effective key that they give us. And this is a little bit tricky. If the table in the spot is undefined, then it will return undefined. That's the way this logical AND works in JavaScript and many other languages. It's kind of conventional. If this is falsy, it just returns the false. But if it's truey, if it's an actual value that's not undefined, then it will return the right side instead. So we're just returning the actual thing that's at the spot. Yeah. This is, by the way, the first, the one here is because we've inserted effective key comma value. So we're just returning the value part, not the entire effective key comma value pair. We just want to, when someone says get me the value for this key, we want to return just the value. We don't want to return the whole pair. Has, like, does this table have a key? Really easy. Just get the key and see if it's undefined. That's the best you can do, really, anyway. Remove the key and value associated with the given key, if any. This is the most complicated method here, and it's a pain in the ass. I can sort of try to go over this. I feel like it's not going to make sense unless you like actually go through it yourself and debug it and stuff, but like in a debugger and look, but sort of the general vibe here is First, we get the effective key out of the key. We don't care about the key. We care about the effective key. We have a convenience function here, which maps indexes to our array range. And we could just mod n, right? Like that's what we've been doing so far. To like, oh, if we go off the end of the array, modding n will wrap it around back to 0, right? But we want negative numbers to wrap around to the end. We don't want just two large numbers to wrap around to the beginning. And that's not the way that modulo works in JavaScript. If you have negative numbers, mod n, then the result will be negative. So we want it to be positive. We want it to wrap around to the end of the table when we go off to the left too far. That's something we're going to be needing to do, is going off the left end of the array here. So we want a separate convenience function that just handles all this for us. And the way we do that is I mod n plus n mod n. That just sort of works out. If you do the arithmetic, you can see. The next thing we have to do, or I guess really the first thing we have to do, is remove the key value pair from the entries array. So we find it. If it's in there, we remove it. Actually, if it's not in there, if the index is -1 out of find index, which indicates it's not there, this is just a predicate that we're doing. We're finding an index where extract effective key equals the effective key that we're actually looking for. So if that result is -1, if it was not anywhere in the table, then we're done, right? Like, it's not actually in the table. So we can just return. And in these like set and get methods, we're just returning this out of the function. That's what JavaScript does in their map implementation, so I wanted to reproduce it. It's so that you can chain calls, like you can say like my map dot remove whatever, dot remove something else, dot remove something else, and it all just chains together because we're returning this each time. But some languages prefer to return the value of the key that was removed, just to like indicate, oh yeah, I actually did remove something. And it can sometimes make code easier to read if you can just check the return value of a remove call. Here we're returning this no matter what, so you can't do that. But it makes chaining nice. All right, and then yeah, we just splice out the one that we found otherwise. That's removing it from the entries array. Now we need to find the effective key value pair. It's just like find spot. I got this implementation down below. It just does exactly what you expect. Just like in the previous methods, we're finding the spot where it goes. We're guaranteed to find it because it was in the array. So we just set that table original spot equals undefined. We've created a hole in our table because we removed it. And now we get to the complicated part of like, how do we backfill this hole with other entries so that we don't break future lookups like we discussed? The approach, at least that I worked out, I don't know if it, like pseudocode in Wikipedia or something is different, maybe, I don't know, or in textbooks. But what I came up with was you look at the, you look backwards to find the previous hole, the previous like empty space in this array. And that's what this does, this for loop. It is going backwards, trying to find an empty hole. If you do find it, then you're done with a loop. And you are guaranteed to find one eventually because you'll wrap all the way around to the one that you just removed. So we will finish this loop eventually. It's guaranteed to terminate. Next step, we're initializing this hole and cur. These will keep track of like sort of where we are. The hole is the one we're trying to fill, and the cur is where we're looking to try to like find something to fill the hole with. So we start with the hole at like the original spot that we just deleted. And then we, our cur is going to start one after that. Whether that's, I mean, if it's already at the end, we wrap around at the beginning, and that's what the wrap is for. Now, here's a for loop where we are, or sorry, a while loop while we are basically looking for an empty spot. We'll keep going until we find an empty spot. Or we loop all the way around to the one that we found when looking backwards. We look backwards to find last hole, like the last hole that we could see behind us. So we keep going until we find an empty spot, or we loop all the way back around to this last hole that was behind us. Those are our termination conditions. Okay, and that makes sense because that's sort of like the range of places that we could find things to fill this hole with. Nothing outside that range could possibly fill the hole because when we go to look it up again, it breaks our lookup algorithm. So we just have to check this particular range. All right. Now, we're looking at the, we're interested in the true hash of whichever item is at cur. So basically, like, where would we have liked to put cur when it was originally hashed if it didn't collide with anything? So we take the key out of this table cur, we hash it, we wrap it. So this is fitting within our hash map, and we get the location that we would like to have put it. And this is basically like this, if you do like the modular arithmetic, what this is kind of doing is saying, is this true hash between last hole and hole? So is it after the last hole, and it might wrap around or whatever, it just has to be after the last hole and before the hole we're currently trying to fill. It took me a while to work out like what the most succinct way to express this is. I think this is it. Two separate wrap calls, and you subtract last hole from each one. You can like write out examples on paper or whatever and convince yourself this works. But we're interested in like in modular terms with this like whole wrapping thing going on. Is the current true hash between the last hole and the hole we're trying to fill? If it's in that sort of space, then, or actually it's the other way around. It's after the hole we're trying to fill and before the last hole. That's right, yes. I'm sorry. It's a little bit tricky. But that's the, those are the values that could fill the hole. Because we're after the hole we're trying to fill, so we may have probed ahead to this further value to find a spot for it when we're inserting it. But we haven't gone so far that we've passed the hole behind us. And we also haven't passed an empty spot. Okay. And then when we find it, we've just filled the hole. And move that into it. Move cur into it. And then we advance cur. We have a new hole, right? So we set the hole to cur, which is the one where we just set to undefined. We've moved something into a hole, so we have a new hole. And at the end of our loop, we're of course just advancing cur by 1 over. And we just keep going until we run out of holes to fill. Run out of holes that we can fill, I should say. Okay, that was a lot. But it does work. Next methods, we have an iterator, a method that returns an iterator called .keys. We call map.keys to just get a bunch of all the keys that were inserted into the map in insertion order. Same thing for values. We're doing this nice little array destructuring assignment. where we can do key comma underscore. We don't care about the second variable here, so we just use an underscore of this dot entries, and it sort of blows up each entry into these two components and gives us a variable named key. Same thing for value. These are generator functions again. We talked about that in the linked list lecture. All right, and here's a last one, an iterator that gives you, like if you'd call a for of loop over the entire map, instead of just calling like map.keys or map.values, then you get this one. And this is just giving you an iterator on the entries array. And in fact, calls the iterator method on that's built into the array class in JavaScript, and just returns that. And then here's just the last little bit of nonsense. Internal, like private methods. Find spot for the effective key. We know how this works. We just check the one that it hashes to, and you know, if it's full and it's you know, we just keep trying the next one and the next one, next one until we get to an undefined, an empty spot, a hole. Or if we actually find the effective key that we're looking for, then that's valid. We find that and we return that. Just keep advancing one every time, mod the table length. And then the last thing here is rehashing. So in our insert method and our set method, we had like if it's past the load factor, then we call grow. And this is what this function is. It just doubles the size of the table, fills them with undefines, and then loops over the entries array and just inserts them all. Okay. I got it formatted as a module, so you can just model that exports equals hash map, and then in the test we can require hash method.js. And yeah, you can just like which one was it? 2024. Oh god. Yeah. You can run this. So we just call a bunch of map.sets and we get them out again, map.get. We can see these are all the keys that were inserted. These are all the values that were inserted. These are all the key value pairs that were inserted. Everything works fine. We remove a few of them. We remove B, D, F, and H. And then you can see what the result of the get calls now. And now our keys in insertion order are missing B, D, F, and H. Here's a complex keys demo where I show how to use objects as keys. So here's our data that we're going to insert. The first key has ID of 0, name Riley Ann, and the value is going to be green. The second key has ID 1, name Sasha, and value gray. And then the third key is going to be ID 2, name Sasha, value red. That's her evil twin. So we insert them all into a hash map that has this extractor function. Object maps to object.id.toString. And that will pull out the ID of each key and key off just that. And we can just get them back again and see that it works. You can see that it's extracting, it's not rendering the object, but it's calling that on the first key of data 2. So it's calling that on ID equals 0. Actually, it's calling .get on the entire object, but we know the function to extract the ID from it. This is our extract effective key function. So it will key off of 0. So it's able to key off of 0 to get green, and that 1 ID to get gray, and that 2 ID to get red, even though the slashes have the same name. because it's only looking at the ID field. That's what we have chosen as our key extractor function. Yeah. Lastly, I do a bit of a hash map versus map head-to-head, where I insert the same values into a hash map as I insert into a JavaScript map. We do 10,000 of them. If, 40% of the time we will remove a key, and 60% of the time we will add a key. And we can, at the end, verify that they have the same keys left over. That's it. It's maybe more complicated than you thought to implement a hash map, but it's also not insurmountable. You can do it. You just have to break it down and address each operation and just think through each one. All right, hope that was helpful.